All right, so here's the deal. So if you look at the equations that we have right now, you have F equals big G, M1, M2 over D squared. So that's kind of the basis of all of the problems that we're going to do. Okay, so this is like, if you have to start over with one equation of all of physics, let's start with this one. Okay, because then we can figure out everything else from there. So from that, then you can get V equals the square root of big G M over R. You've got little g equals big G M over R squared. And then that Swiss Army knife equation of big G M T squared 4 pi squared R cubed. Now, here's the most important thing about every one of these equations, okay? This is like the quintessential MKS system. Everything that you put in here has to be in meters, kilograms, or seconds, okay? It's the only thing that works. You cannot put in days, you cannot put in hours, you cannot put in astronomical units, because these aren't ratios, okay? These are actual calculations. So the one common theme that is true of all of these is that value, that value of big G. So one of the things you're going to have to be able to do on the test, for example, is that I'm going to give you one of these equations. And I'm going to say, hey, do dimensional analysis and prove that these units actually work. So I might say, okay, let's start with this one. Where I'd say, okay, if you solve this one for t, you'd have the square root of 4 pi squared R cubed over big G M. Now, let's talk about the M that's here, here, and here. Is that M the mass of the satellite, the mass it's following, or is this the mass of the planet that's at the center of that orbit? It's always the mass of what it's following towards, okay? This is not the mass of what is in orbit or the mass of what's following. It is always what is at the center of that orbit. It could be, you're talking about the Earth going around the sun, oh, that's going to be the mass of the sun. If you're talking about a lunar command module orbiting around the moon, that's going to be the mass of the moon. So I will never, ever, ever give you the mass of the satellite. You know why? It doesn't matter. I'm not going to tell you that it's painted silver or the fact that it has a really cool American flag on the side. No, okay? I'm not going to tell you any of those things because it doesn't matter. Now, on all of these, from what point does that radius have to be measured?
The center of the
From the center, not from the surface, okay? So that's going to be vital, okay? It has to be from the center. So if you look on that, like for example, on number 8, okay? So you got to determine the approximate speed of the lunar command module moving a circular orbit at a height of 72 kilometers above the surface of the moon. I gave you the radius of the moon. It's like on number 8, you've got to take those 72 kilometers, add that to 1738, okay? Because it has to be from the center of the moon out to wherever that object is, okay? Keep that in mind. So let's say, back to this problem, let's say, all right, I'm going to give you this equation and say, prove to me that you're going to have to be, that this thing produces units of seconds, okay? So let's work through this one so everybody kind of sees how this deal is going to play out. Do you have to worry about the 4 pi squared?
No.
No, okay, it doesn't have the units. But that meters is going to, or that radius is going to be in meters, but that's going to get cubed. So up on top, I've got cubic meters. That's the only thing that I have, okay? Cubic meters, that's it, nothing else. Now, what are the units on big G? Well, newtons meter squared over kilogram squared. If you're not sure, look on your equation sheet, right here. There are the units, newtons meter squared over kilogram squared, okay? So then I've got the mass is going to be in kilograms. So start with that. Let's put in the units. So what can I get rid of at this point?
The kilograms.
I can get rid of one of the kilograms, and I can get rid of, so at this point we're going to rewrite this and go, okay, I've got meters, and then I've got newtons over kilograms, right? That's what I have left after that initial cancellation. So then, what can I do with those meters since I can't cancel those out? What's another way to put newtons?
Kilograms, meters.
Kilograms, meters per
Second squared.
times, and then all of that's divided by kilograms, right? Okay, because that's up there, that's newtons per kilogram, right? So then, I'm going to cancel out one of those kilograms, so now that's gone, right? So what I would recommend at this point, I'd write that as meters over 1. What's the inverse of meters over second squared?
Second squared over meters.
Second squared over meters. A miracle happens. I get the square root of second squared. I get seconds. Okay? So, here's how you can guarantee you get these points on the test. Because I'm going to tell you right now, I'm going to pick either the velocity, little g, or this equation, and ask you to do dimensional analysis. And I'm going to tell you right now, the whole key is that at some point with those newtons, you have to substitute in kilograms meters per second squared. So, if you want to make sure you get these points, practice this, because you know it's going to be one of these three. So it's just like, oh, let me make sure that I can do all of those. And then if you feel good about it, hey, you're good. If you're not, then work them again and again and again until you do get good at it. Okay. So, with that said, let's say hypothetically that I gave you this problem here on the test. Hold on, let me get rid of all this. Okay? And there's problems like this on the assignment. Okay? Just make sure everybody's cool with what we want here. So here's your setup. So we got a satellite 122 kilometers above the surface of the Earth. Okay? And I want to determine the velocity, the orbital period, the centripetal acceleration, and little g. I always said if I was going to be a rapper, that would be my stage name, little g. But I'm not. So, what's the first thing that you're going to have to do with 122 kilometers? Change it into meters. Then what are you going to have to do?
Add it to the radius.
Add it to the radius of the Earth. So somebody using the miracle of modern technology, take 122, multiply that by 1,000, and add that to the radius of the Earth.
640, wait.
So let's have a little scientific notation. And don't round this thing, okay? Do not round this radius. You keep all of these digits. So what do you get as the radius?
6.4933.
6.4933
00.
times 10 to the 6th. The rest are zeros? Okay. All right. So I need to calculate the velocity. So that's going to be big G, mass of the Earth divided by, now again, before you do any calculations, velocity of near-Earth orbit satellites, what order of magnitude should my answer be? 10 to the third, okay? Orbital periods, 10 to the third, okay? All you have to remember is 3. So if you do this calculation and you don't get something times 10 to the third, you have done something wrong. And in the name of time, you don't need to write out 6.67 times 10 to the negative 11th. You don't need to write out 5.979 times 10 to the 24th. I know what these numbers are, okay? But at least say, hey, this is what we're going to do. Now, if you like writing those numbers out, hey, fine. It's fantastic, okay? Beautiful. Or you can just put big G, mass of the Earth, okay? Now, if you really want to be efficient, if you look at what's common to all those equations, at the end of the day, you multiply G times the mass of the Earth, okay? That's what you do. So, if you wanted to store the big G times M as a separate variable in your calculator, then that would actually, if you, it's not, you don't have to save you that many steps, but big G times the mass of the Earth is a very, very common calculation. Now here's what you're going to do wrong. You're going to get this and you're going to be so excited, and then you're going to forget to take the square root. Okay? Seen it? Been there? That's why I said when you get this velocity, just ask yourself, hey, is this 10 to the third? If it's not, something has gone horribly wrong. Okay, so what do you get out of this?
7.85
So 7,850 meters per second. And remember, okay, we have to be going that fast because that's, like here's this model of the Earth. If you're going to be on top of a mountain and you throw that apple, it's going to travel a certain distance. But if you throw that apple fast enough, then it's going to be in this state of free fall as it goes around the Earth. And that's what happens, right? That's why you have to be going so fast to make that happen. And like we talked about yesterday, that's roughly about 5 miles per second. Okay, so you're hauling the mail. Okay, so there's our velocity, 10 to the third. Okay, that's cool, right? So then we need that orbital period. Now remember, what you have on your equation sheet is this GMT squared equals 4 pi squared r cubed. So you've got to be able to solve this equation for any of these variables. Get t, get mass, get radius. Okay, so this is why this is like the Swiss Army knife equation, because you can use it to solve so many different things. So, Kelsey, I need this solved for t, so what am I going to do?
Divide by GM, big G times M, and then square root that sign.
Fantastic. Okay, so in this case I'm going to have 4 pi squared, and we've got that radius of 6.49 divided by big G mass of the Earth. Now, if you really wanted to get hardcore efficient nerd, okay? This is just an option. If you think about it, that 4 pi squared big GM is a constant, okay? As long as you're in a near Earth orbit, that number is not going to change. Okay, so you're not going to change big G, obviously, and you're not going to change the mass of the Earth. So what you could do, and again, you'd have to be hardcore nerd to do this, but you could get this number by itself, but here's what is important. So that would just be some constant times r cubed. So then the only thing you'd have to do is, if you have that constant, you just have to take the square root of r cubed and multiply it by that constant. Boom, it would save you punching in 4 pi squared times big G mass of the Earth every time. But again, if you're doing this calculation a lot, like you're an engineer that does satellite calculations, yeah, just have that K by itself. This one, probably not so much. All right, so what did you get for the orbital period? And don't forget to cube that radius.
(5.21 times 10 to the third).
What'd you get?
5.21 times 10 to the third.
So 5,210 seconds. Now divide that by 60.
86.8.
So 86.8. Oh, come on. Minutes. So that's about an hour and a half. Okay. So if you're in a near Earth orbit, it takes about an hour and a half to go around. So what that means is, if you really like sunrises, okay, be in the International Space Station. You're going to see a sunrise every hour and a half. Okay, because that's how often you're going to be going around the Earth. So if you really like this, like, oh, I like sunrises. Okay, fine. Go in the International Space Station. You're going to see one every hour and a half. But the problem is, it kind of messes with your sleep cycle, because you're used to, going night-night, and we're going to have 8-10 hours of darkness. Well, up there, you're not, because of the fact that you're making a loop every hour and a half. All right, so we got that one done. So let's remember these numbers, because we're going to need them for the next one. 7850 meters per second in a period of 5,210 seconds. All right, so let's get rid of all of that.
And Burkett, I told you the wrong number.
For
It's
what?
7840.
Huh?
It's 7840.
On the velocity?
Yeah.
Okay.
We'll just go
I
with
even
it.
wrote for it, I told you about it.
I did all the calculations with that.
Okay, we're all right. It's close enough. As long as we got the idea.
We did the calculations right, just the wrong number, that's all that matters.
What's a zero between friends?
A lot.
It could be a lot. Do I owe you $10? Do I owe you $100?
Yeah.
Okay. So, we got the first two done. We got the velocity and the orbital period. So now let's talk about centripetal acceleration. So first off, how do you know that it's undergoing centripetal acceleration?
Because it's an orbit. It's not
Moving in a
going
circle, right? Otherwise, it would be moving in a
Straight line.
straight line. Okay. Now, there's two ways you can calculate centripetal acceleration. What's one of them?
V squared over R.
I could use v squared over r, okay? Or I could use r over t squared. Which one do you want to do? Okay, fine, we'll use v squared over r. So we got 7,840 meters per second squared, and then what was that radius?
4933 times 10 to the 6th.
Okay, now, before you do any calculations, let's just get a ballpark. This is 10 to the third squared, which is going to give me 10 to the 6th. 10 to the 6th divided by 10 to the 6th gives me 10 to the 0, right?
Yeah.
Okay, so I got to figure it's going to be a fairly small number. So if I do this and I get a really big number, I've done something horribly wrong. Okay? So, what do you get out of this?
$9.47.
9.47? So, if you were in that satellite, okay, that would be the centripetal acceleration that you would be experiencing. Okay? It's cool. Now, let's calculate little g at this point. Now, here's the visual that I need you to get on this calculation. So imagine that here's the Earth, and we're going to build this really tall tower that is 122 kilometers tall. Okay, so that's roughly about, 50 miles. So imagine that we're going to build a tower that's 50 meters tall, or 50 miles tall. That, if you've driven like the turnpike going up to Kansas City, that would be about from here to Cassidy. Okay, so if you kind of get that visual, that'd be about 50 miles. Okay, so imagine that we're going to build this tower, and here's the visual that I want. We're standing on top of this tower, and we're going to drop a ball, and we're going to try and figure out what that gravitational acceleration is going to be. Now think this through. If you're here at the base of the tower and you drop this apple, what's the acceleration going to be? 9.8 meters per second squared, right? Now, imagine we're standing on top of this tower that's 50 miles tall, right? When I drop that apple, is my acceleration going to be bigger or smaller than 9.8 meters per second squared? Smaller. So you got to figure when I do this calculation, my acceleration should be less than 9.8 meters per second squared because I'm farther from the center of that gravitational field. Okay? So if I do this calculation and I get an answer bigger than 9.8 meters per second squared, I've done something wrong. Because as big as that value is going to be, is right at the surface of the Earth. So this is why when we talk about little g changes. Okay? Depends on where you are on the Earth. Top of Mount Everest, it's going to be different. You're in Kansas, that's going to be different than even like Denver, Colorado is. So there's going to be some variations on this. Okay, so the only way we can get little g is to go big G, mass of the Earth over r squared. Now, if you plug in the radius of the Earth, 6.3713 times 10 to the 6th, right here, the radius where we're at now, you're going to get 9.8 meters per second squared. But we're not at the surface. We're a long way out. So we're going to be dividing by a bigger number. So my g should be a little bit smaller. Okay? So somebody take big G times the mass of the Earth divided by that 6.4933 times 10 to the 6th meters squared. And let me know what you get.
I got 9.46.
Ooh. Which is basically the exact same as that answer is. Coincidence? No, not at all. Here's the deal, okay? These numbers are the same. My centripetal acceleration is going to be the same as my gravitational acceleration. Here's the reason why, okay? Since the beginning of this whole argument, okay, the whole argument hinges on one idea. And that's that my centripetal acceleration, or my centripetal force, is created by my gravitational force. Okay? That's the whole idea. That without a gravitational field, I don't have an orbit. Okay? And these two values have to be equal. That's one main idea that you have to get out of this whole thing. Well, centripetal acceleration is just mass times my centripetal acceleration. And this Fg is just going to be mg, right? Okay? Which is also big G, m1, m2 over d squared. So all three of these are equal. Mass times my centripetal acceleration, mg, big G, m1, m2 over d squared. Now, here's the one common thing. This is Kelsey's mass. What's going to happen to Kelsey? She's going to drop out. So right away you realize, oh, look, my centripetal acceleration is equal to my gravitational acceleration. Okay? So that's why those two numbers match up. So and here's the visual, okay? So imagine that you're standing on top of that tower on the Earth, okay? So what that means is if I drop this apple, it's going to have a linear acceleration downward of 9.47 meters per second squared, okay? Now, what that also means is if I could take that and throw it at whatever that velocity was, 7,840 meters per second. So if I could throw this thing out at 7,840 meters per second, that would be then my centripetal acceleration as it's falling around the Earth. Okay? So that's one of the main things that you have to understand. Like, oh, wow, this is kind of cool, right? This all makes sense. These two values, right, that centripetal acceleration and g, are equal to each other, and they have to be, because gravity is the only thing available to create that centripetal force. Okay? So when I ask you to calculate the centripetal acceleration of an orbiting object, you could either calculate the centripetal acceleration, or you could calculate little g. You're going to get the same answer either one, because the two things are equal. All right? Got that. Okay. So, let's say, and I promise you, you're going to have a question like this on the test, and there's one like this on your assignment. Okay? So, here's the deal. So, we've got this moon, all right? So, here's this visual, here's the moon. Has an orbital period of 20.5 hours. A radius of 3.68 times 10 to the 6 meters. What's the mass of the planet? So what's happening is that we found this moon that's orbiting Saturn, Jupiter, whatever it is, okay? And we know the orbital period, 20.5 hours, which is pretty fast. I mean, considering the fact that our moon takes like 27 days to make one loop around, this is pretty quick. Okay, so that's 20.5 hours. We've got the orbital radius. Now, here's the deal. You have to also watch the terminology. When I say it's the orbital radius, you don't have to add in the radius of the planet. Okay? If I tell you that's the orbital radius, That is the distance from the center out, okay? The only time you have to add in the radius is if I tell you, oh, it's 5 kilometers above the surface, okay? So if I tell you it's the orbital radius, don't add anything to it. That is the number. The only time you have to add anything is if I say it's a certain distance above the surface, okay? So that's the number, boom, here you go. So I want to find the mass of the planet, and this is very applicable. This is how we find the mass of planets, is that we obviously can't weigh the planets themselves. So we make observations about things that orbit them, and then we work backwards and we calculate the mass. Or we land on the planet, or the moon, or whatever it is, and we make and we figure out what little g is, and then we can work backwards and find the mass of the planet there. So what we have to do is we have to make observations about the gravitational effect that it has on objects, and then we work backwards from there. Okay, so what are we going to start with on this problem? Mr. Johnson, what am I going to start with?
Probably using radius, the mass 4 pi squared r over t
Beautiful.
squared.
Yeah, that's the Swarmy knot. So I got 4 pi squared r cubed equals big G m t squared. So it's the only thing I don't know,
Yeah.
mass. So I'm going to divide by gt squared, right? So I got 4 pi squared. I've got my radius, 6 point or 3 point, dyslexic today, 3.68 times 10 to the 6th meters cubed. And then I've got big G. Now, what am I going to have to do with those 20.5 hours? Change it into seconds, okay? And you all sit there and go, oh, Mr. Burkamp, we'll do that on the test. You lie. It's the most blatant lie you all will tell me all years. You're going to see those 20.5 hours, and you're just going to blissfully write that down. And it won't work. And here's the reason why. The only unit of time that exists is hidden within this G, which has newtons, which are kilograms meters per second squared. The only unit of time that exists is within this newton, and that's second squared. That's why you have to convert those hours into seconds. The only time you could keep hours as hours is if you were doing Kepler's third law, where it was a ratio. So anytime you see big G, I cannot emphasize this enough, you have to change that time into seconds. It's the most common mistake. Y'all don't struggle with the kilometers. Y'all don't struggle with kilograms. But it's that conversion from hours into seconds or days into seconds. That's what you all tend to forget. Okay, so I got 20.5 hours. 1 hour is 3,600 seconds. And the other thing that you're going to forget to do is you're going to forget to square that. Okay? Seen it 100 times, that's what you're going to do. You're going to forget to square that. Now, when you do this, when you convert these hours into seconds, if you're going to do that as a separate calculation, don't round these seconds. Okay? Do not round these seconds. Keep all of them. Round when you get to the bitter end. Okay? All right, so what do you get?
7.38 times 10 to the 4th seconds.
Yeah, but I mean as far as like the overall answer.
Oh, never mind.
0.02 times 10 to the 10th.
What'd you get?
Ooh, I don't know for that though.
To the seconds?
For the overall. Oh, I got 6.02 times 10 to the 10th.
I was just doing seconds.
You get that from?
Yeah.
I'm doing it
Let's
right
do it. I don't feel
Who's blind? What did you get him?
Yeah.
I got 6.02 times 10 to the 10th.
I got 5.42 times 10 to the 21st.
Hold on.
There's a little bit of difference. 10 to the 11th.
Let me Hold on. Let me
Well,
calculate.
look at this, order of magnitude. 10 to the 6th gets you what? 10 to the 18th, right? 10 to the 18th divided by 10 to the negative 11th gives me 10 to the 29th, okay? And then this is roughly 10 to the 3rd squared, so that's like 10 to the 6th. 10 to the 29th divided by 10 to the 6th gives me about 10 to the 23rd.
Yeah.
So I gotta
Probably
figure that
right.
this is way wrong.
That's 5.41.
I don't know what I did.
I can't see this.
What'd you get?
What you do with that?
That's what I got,
5.41 times 10 to the
Yeah.
21st.
What'd you get? That's what you got?
That's what I got.
Okay.
I don't know what I did. Hold on, I'm recalculating.
So, that's why I said, in this unit, you have the potential to get answers that make no sense whatsoever.
So
No?
triple.
5.41 times 10 to the
21st.
kilograms. Okay? Cool with that. All right. Now, we have
Ow.
one problem left, and if we can do this one, then I'm feeling good about life, okay?
Oh.
Luke, what'd you do?
Yeah, what?
So,
No, I was just looking at something.
here's this moon. We land on it. We set up a pendulum. We figure out that little g is 1.22 meters per second squared. We've got the radius of the moon, so I need to figure out the mass of the moon. So this is exactly what happened with the Apollo 11 crew. The first thing that they did, they set up a pendulum. They measured the value of little g on the moon, and then they found the mass of the moon, which is kind of cool if you think about it. Like, okay, we landed on the moon, we didn't even know the mass of the moon. So that's kind of cool. So, and we'll talk about the moon launch here later on, but to kind of give you perspective on how tough that is to even get to the moon, imagine you're on one end of the football field, okay, and you have an apple, okay, that's on the other end of the football field. And this apple is moving, okay? This is stationary, it's moving, because it's just like, you know, when we launch to the moon, we can't launch where the moon is. We have to launch where the moon's going to be when we get there. It's like throwing a pass. You know, if I want to throw a pass to Ryan, and she's running across the middle of the field, I'm not going to throw the ball to where Ryan is. I'm going to throw it where Ryan's going to be. So, imagine that you have an apple. You are opposite ends of a football field, 100 yards away. The apple is moving, you have to shoot it with a .22 rifle, okay, little small rifle, and you don't want to hit the apple. You just have to nick the skin of the apple. So that's the equivalent challenge that they faced in trying to get a lunar command module to the moon and caught in its orbit. You're hitting an apple 100 yards away that's moving, and you have to nick the skin, okay? You don't want to hit the middle of the apple because you don't want to crash this thing into the moon. You want to get this on the edge of it, so then you slow it down so it gets caught in that orbital field. Okay, so I want to find the mass of the moon. So what equation are you going to start with? What'd you say, Fu? Little g equals big G m over r squared. What's the only thing I don't know? No, I know the radius. That's the only thing I don't know. Mass. So, I get Gur squared over big G is going to equal mass. So I've got 1.22 meters per second squared times the radius, 1.40 times 10 to the 5th. And that's going to get squared, and then I'm going to divide that by big G. So what do you get from the mass of the moon? Let's see if we can see how far these numbers are.
I don't know. I know what I did because I wrote G and it's like, oh, it's 6.
Okay.
And it looks like
There's a little
6.
bit of difference.
And I didn't, yeah.
Don't forget to square the radius.
Okay, that wasn't really pressure.
Aiden?
Pressure.
3.59 times 10 to the 20th.
That's what I got.
Okay. Kilograms.
did it right,
That's cool. Okay. All right. And literally, that's what you do. Okay? When you're trying to find the mass of a planet or a moon, you figure out what little g is, you work backwards and you find the mass. Okay? That's what you do. Now, let's talk about this. I want to know how far I have to go from the center of the moon so that a 1 kilogram mass weighs 1 Newton. Okay? So, if I'm standing at the surface of the moon and I've got a 1 kilogram mass and I hook it up to a Newton scale, what's that going to read if I'm standing on the moon? Do not make this difficult. You all are making this difficult.
Repeat the question.
1
Okay.
Newton.
If I'm standing on the surface of this moon, okay, and I have a 1 kilogram mass, and I hook it up to this Newton scale,
Do 1.2.
what's it going to read if I'm standing on the surface of the moon?
1.22
1.22 newtons. Why?
because that's
If I take 1 kilogram times 1.22, oddly enough, I get 1.22, right? It's kind of a radical concept. So, here's the deal. I want to figure out how far I have to go from the center of this planet, or moon, so that when I hook it up, it's just only going to read 1 Newton. So obviously I have to be above the surface of the moon, right? Because if I'm at the moon, it's going to read 1.22. Now there's 2 ways you can do this. Okay, I don't care. Now that we know the mass of the moon, so one option is that you can go, well, I want that 1 Newton mass to feel, or I want that 1 kilogram mass to feel like it weighs 1 Newton. And that could equal big G times the 1 kilogram mass times the mass of the moon, 3.59 times 10 to the 20th kilograms, divided by r squared. Okay? Because that's, fundamentally, that's what's going to happen. So, I want that thing to feel like it weighs 1 Newton. Oh, okay. And because that's what that F is going to be. Oh, that's that gravitational force. I know what big G is. I know one of the masses is 1 kilogram. I know the other one is the mass of the moon. The only thing I don't know is r squared. So basically, you're going to multiply by r squared, divide back by 1. The 1's going to cancel out. And then you're going to do what? Take the square root of it, boom, there you go. Okay? So that's an option. Okay? So conceptually, that's what that number means. Okay? Because when you're talking about what something weighs, at the end of the day, it's a measure of that gravitational force. Okay. So that's kind of big idea. Ah, right. What creates weight? Oh, right. It's gravitational force. Okay. That's what I want it to be. Okay, cool. Plug in the numbers, there you go. Now, what's another way that you could work that problem? There's the other one's actually a little bit simpler. What do you want little g to be so that a 1 kilogram mass weighs 1 Newton? What do you want little g to be? 1. So you want little g to be 1 meter per second squared. So you go, oh, little g equals big G, mass of the moon over r squared. Do you know what little g is? Yeah, 1 meter per second squared. You know what big G is, you know the mass of the moon, so guess what? You go, oh, r is going to equal the square root of big G, mass of the moon over little g. And basically you're going to do the exact same math, okay, because if you look at this little g is 1 meter per second squared, okay, which is basically what's going to happen up there, because those ones are going to, they're ones, but they're ones. Does that make sense? So you don't have to worry about it. So basically, it's the exact same math. You just change how you do it. Okay? So anyway, so what do you get as an answer?
I got 2 different answers for doing.
What'd you get?
I got 2 different answers between the 2 different ways.
No, you should
Yeah.
get the same one either way.
Because you're dividing by 1 other way, right?
Yeah.
I got 1.55 times 10 to the 4th.
Now, what does your answer have to be bigger than? Well, it's got to be bigger than the radius of the moon, right? Okay, so you know your answer has to be bigger than 1.40 times 10 to the fifth. Now, how could you tell if this answer is right? What could you do to work backwards? Well, you could go back up to this equation and go, oh, let me plug in that radius, big G, plug in the mass of the moon, recalculate little g, see if I get 1 meter per second squared. If I do, hey, it's cool. If I don't, it's been a train wreck. Okay? So that's how you can check that that answer is right. Or, if you really wanted to go old school, you could go to that big equation for FG, plug in big G, plug in 1 kilogram, plug in the mass of the moon, plug in that radius, see if you get 1 newton. If you do, you did it right. Okay, so that's the other way that you could work the problem to see if it's correct. Okay, so if you can do all of those and feel good about life, we're okay. Now, let's talk about a historical perspective. Okay, so Aristotle, Bible, everybody says, hey, we're an Earth-centered solar system. We're good. We feel good. God made man in his own likeness. Everything falls towards us or circles around us. We're the bomb. Okay? It's this freshman mentality. We feel good about ourselves. Mom sends a note every day that says, you're special. Love you. Okay? Copernicus comes along and says, no, this is stupid. Okay? Observations don't make any sense. How do we explain epicycles? We've got everything jacked up. This is too complicated. Let's put the sun at the center and have everything revolve around us. That made people unhappy because mom now sends a note that says, you're not special, you're just like every other kid, I've been lying to you. It's like, oh, seriously, mom, okay? So now we're kind of crestfallen. It's like, oh, we're not so special. But the observations fit. Tycho Brahe collects all the data. Kepler steals it, comes up with his 3 laws of planetary motion. That's early 1600s. Newton comes along, mid to late 1600s, says, hey, here's how we can explain gravity. Oh, F equals big G, M1, M2. Oh, things orbit in a circle. Same force that makes an apple fall is the same force that makes the moon fall towards the Earth. Okay, cool. All right, we got this. We're good. And everybody's happy at this point. But nobody really understood why it worked. Okay, yeah, the equations work, but like, what is gravity? Because you could make the argument that it's kind of like magic, you know? It's like, oh, I dropped this apple. Why does it fall? Oh, it's magic. Well, because if you reverse the process, and if I put my hand over it and that apple started to go up towards my hand, you would go, oh, that's magic, because there's no observable force that's making it go towards my hand. So if it goes up towards my hand, oh, that's magic, and I'm a witch and will burn me at the stake. But if I hold it and I let go of it, oh, that's just gravity. So in one situation, it's this natural phenomenon of gravity. The other situation, I get burned at the stake. Okay? Only difference is which direction does the apple move. All right. So Einstein comes along. Okay, so now we're going to fast forward about 300 years. Now we're in the early 1900s. Einstein publishes work, General Theory of Relativity and the Special Theory of Relativity. So what he viewed Earth as a fabric of space and time. So stop that camera. Unplug it and bring it. Okay, so this is just like spandex, okay? So it's kind of stretchy. So Einstein viewed space and time as like a fabric, okay? And he was the first one to weave this concept of space and time together. So you can actually do a lot of kind of cool physics in terms of even Newton's laws of motion. So I take this little marble and I roll it across. You'll notice that it pretty much travels in a straight line. Okay? Oh, that's kind of Newton's first law. Oh, objects in motion remain in motion. Things want to travel in a straight line. Okay. Until an outside force acts upon them. Now, imagine now this is like the sun at the center of our solar system. So what's going to happen is that large mass creates like a gravitational well. Okay? So one of the things we talked about is that Mother Nature is a lazy prima donna. So Mother Nature is only going to end up at the lowest possible energy state because that's the easiest thing to be in. So now when I roll this marble, now what happens is that you'll notice it travels in a curved path, whereas before it traveled in a linear path. So the argument is that when you see something orbiting the Earth, it's basically riding a ridge in a space-time warping. So as you get further from the center of that well, space and time is warped less. So the gravitational field isn't as strong when you're close to it. So if I roll this marble up there, okay, and as it gets closer and closer and closer, that warping gets more and more and more severe. So you're deeper and deeper and deeper into the gravitational well. Now, the other thing that you can actually do is you can actually look at this in terms of Newton's third law. Because everybody focuses on the small marble. But if you notice what happens when that thing goes by, that bigger marble actually moves just a little bit. Okay? Not a lot, but there's a noticeable wobble to it. Because everybody says, oh, you know, gravity is pulling on this. And it is. But by Newton's third law, gravity is pulling on the smaller marble, but the smaller marble is actually pulling on the bigger one as well, with an equal and opposite force. But it just doesn't move as much, because it has a much larger mass. So when that thing goes by, there's a very subtle wobble to that bigger mass, because this is also warping space and time. So all of you right now are warping space and time. Okay? Not very much, but you're warping it a little bit. So on your college application, you can say, oh, what's your superhero strength? Oh, I warp space and time. Well, it's cool, everyone does, so it really isn't something unique to you. So, let's say that we want to go to the moon. So, here's the Earth, and there's the moon. Now, so the Earth has much more mass than the moon does. Okay, it's a deeper gravitational well. So if we're going to go to the moon, here's the basic sequence. So they launch, they orbit around the Earth a couple times, make sure everything's cool, right? Then they fire the engines and they coast towards the moon, and then they get caught in that orbit. They orbit around, they send the Lunar Command Module down, you still have someone orbiting the moon, they get done, they come back up, they re-rendezvous, they fire the engines, and we go back to the Earth. Okay, so that's the short version of a very, very complicated story. Because keep in mind, number one, the Earth is moving around the sun. The moon is moving around the Earth. So you're trying to hit a moving warping of space and time as this thing is going through the space, and the Earth itself is moving as well. So this makes it look very simple. It's horribly, horribly complicated. Now, one of the things you're going to do in your assignment is you're going to calculate what's known as two Lagrange points. Okay? Lagrange points are points where if you put an object, it will remain stationary and locked in place relative to the motion of the Earth and the Moon. So this is kind of the cool in terms of if you view it in terms of a gravitational well. So the first Lagrange point is the point where you have a tug of war between the Lunar Command Module, the Earth, and the Moon. So I want to find a point where when I put it there, it's pulled equally towards the Moon and it's pulled equally towards the Earth. So is that going to be in the middle, closer to the Moon, or closer to the Earth? Luke Taylor.
Earth.
Closer to the Earth? Okay. Everybody cool with that? No? Aiden, you shake your head no. Why?
Closer, because the gravitational pull is stronger on Earth, so if you're closer to it, you'll be more easily pulled in, so you would want to be farther from it and closer to the moon.
There you go. Because what's going to have us, which one has more mass? The Moon or the Earth?
Earth.
Earth has much more mass, right? So, and here's how I can do this. If I put this marble halfway in between and I let go of it, what's it going to do? It's going to roll back towards the Earth. If I put it too close to the Moon, it's going to roll towards the Moon. So what I'm going to try and find is like the middle of this gravitational well. Okay, so I've got a shallow gravitational well here, and I've got a deeper gravitational well here. So that midpoint is going to be basically the ridge in between the two wells. Okay, So if I put it like something like this, okay,
Whoa.
right? So, it's not my first rodeo. So at this point, this is what we're going to call the first Lagrange point. So the spaceship at that point, it's not in zero gravity, okay? It's still being pulled by the Earth, and it's still being pulled by the Moon. But now it's an equal balance. Now, one of the things I want you to get out of your mind is that, oh, when it's going away from the Earth, it's only being pulled towards the Earth, okay? No, it's being pulled towards the Earth, but it's also being pulled towards the Moon. And even when we're going around the Moon, guess what? We're still being pulled towards the Earth. So what you have to do is actually, it's pretty complicated. When you cross that point, you're going to begin to speed up. Because now you're like on the downhill side of the gravitational well of the Moon. So then, what they have to do is they actually have to fire the engines. They have to slow down the Lunar Command Module so that it gets caught in the orbit of the Moon. Because if you're going too fast, you're going to shoot past it, and then you're going to start this big, huge elliptical orbit. So that you have to slow down and get caught just so you can ride that ridge of that gravitational well. You circle this, you come back, boom, you come back, land on the Earth. Got that, how that plays out. Now, where it gets weird is when you have like a binary star. If you have a binary star, where you have two deep gravitational wells, oh, come on, really? Here we go. Now when you try and do an orbit,
Whoa.
you got some really kind of weird things going on. Okay? Because now, so that gets really complicated if you want to calculate like the orbital path of a planet or anything around two gravitational wells. Then you've got, because what's happening is that, okay, now you're very much pulled by both of them. So that force is always changing based upon that location. Okay, so one more. All right, got the idea? Good, great. Okay, back we go. Here's the Moon.
You can bring your sweater too, Josh.
Okay, so we orbited around the Earth a couple of times, made a couple of laps, boom, we're coasting towards the Moon. And there's two possible Lagrange points, L1 and L2, which is on the other side of the Moon. Now, I'm going to get you started on this, and I'm going to show you two potential ways that you can solve this problem. I don't care which one you do, it's up to you. But here's the basic idea, is that on this first Lagrange point, the gravitational force back towards the Earth is going to equal the gravitational pull towards the Moon, okay? If you like visuals, you're at the top of the gravitational well, okay? It's like you're on the top of the hill, okay? If you go towards the Earth, you're going to roll downhill. If you go towards the Moon, you're going to roll downhill. So I'll send you this video, Luke. So that's what so you're at the top of this hill, and that's what you're trying to find is the top of this hill. Okay. So no matter how you do it, you're going to start with the basic idea that the force between the Lunar Command Module and the Earth is going to equal the force between the Lunar Command Module and the Moon. Okay, so that's the basic idea. Now, I tell you that the entire distance between the Earth and the Moon is, I think it's 3.844
Yeah.
times 10 to the 8th.
Yeah.
How did you just remember that? I guess you created the assignment.
Yeah, well, I did, yeah.
Like, how do you
And the
just,
mass of the Moon is what, 7.22 times 10 to the 22nd? Because that's up there in another problem. Oh, 7.35.
Wow, boo.
My bad, my bad. I got to the 22nd part right.
not important.
Okay, yeah, you screw up one time. 9 right, what do they remember the one time you screwed up? Okay,
Because it's significant.
now, so let's just focus on calculating this force, right? So I'm going to have big G, mass of the Earth, times the mass of the Lunar Command Module. Now, I don't know what this distance is, so what are we going to let that equal? X, okay? But that's going to get squared, okay? That's going to see some distance. I don't know what it is, we'll figure this out. Now, that has to equal big G, mass of the moon, times the mass of the Lunar Command Module. Now, what is left, if this distance is x here, what's left over?
Oh, it's the distance minus x.
Yes, it's the entire distance minus x, okay? So, that's going to be that 3.844 e to the 8th minus x, but that's going to get squared, okay? Go with this. Now, what's going to happen to the mass of the Lunar Command Module? It's going to cancel out. You know why I didn't give you the mass of the Lunar Command Module? Doesn't matter. Okay? Now, it matters if you're going to try and launch it. You have to know the weight there. But in this situation, doesn't matter. What about big G?
Gone.
Gone.
Oh.
So something that looks horribly complicated actually reduces down to something pretty simple. So at this point, I'm going to cross multiply. So I'm going to have the mass of the Earth times 3.844 e to the 8th minus x quantity squared is going to equal the mass of the moon times x squared. Okay? So all I did was cross multiply because I hate fractions. Okay? That's all I did. So I just cross multiply. Now, you know the mass of the moon, 7.35 times 10 to the 22nd. Okay, gotcha. Okay, mass of the Earth, 5.979 times 10 to the 24.
24.
Okay,
Period.
so if we could ever have like Jeopardy of physical constants, oh, I'm all in. Okay, so
You'd win that one.
what I want to do is I want to get x squared by itself. So I'm going to divide by the mass of the moon. So somebody take the mass of the Earth, okay, pull that up on your calculator, and divide that by the mass of the moon, 7.35 times 10 to the 22nd. It's a harsh crowd, man. I screw up one mass of the moon. Oh, you're a horrible person.
Oh, we never support the person. We support.
Well, that was implied.
we did.
No, I took that from Kelsey and Zach, that I'm a horrible person.
I'm
Yeah.
glad you understood.
Oh, yeah, God, I pity your husband.
Hey.
Too. It's like, oh, you screwed up one time.
I got 81.3.
Now, let's actually give me one more digit.
Okay, 81.35.
81.35.
I could be wrong. Someone double check me.
No, it's
You should
right.
remember that. Yeah.
I do, I remember that, it's 81.35. So what that means is that the mass of the Earth is 81.35 times more massive than the moon is, okay? So that's a pretty big difference. So, at this point, I've got 3.844 e to the 8th minus x quantity squared equals x squared. Okay, so this is where we're at right now. So here's your two ways that you can solve this problem. Okay, how you do this is up to you. Okay, I'm going to show you both methods. Do you want the easy one first or the hard one first?
Hard.
Okay, I heard the harder one, more difficult one
Wait, I have
first.
a question.
What?
Why don't you have to divide the big quantity squared by the mass of the moon too?
Yeah.
That
Divide
might be really
what?
Oh, that was a joke. That was a joke. I figured it out. Just kidding.
Okay,
Yeah.
we'll blame it on the sweater.
I got it.
Okay.
It's
All right.
not. It's not pink.
I didn't say it was pink, but it's not orange. Okay, so here's the deal. So let's make this simple. Pretend that you're back in Algebra 1, and I ask you to expand the binomial 5 minus x.
Oh no.
What do you get?
X
squared.
X squared
Minus 10x plus 25.
minus 10x plus 25, right? Y'all remember that? So here's option number 1. You expand this binomial. Okay? So you're going to get x squared, take this times 2, that's the number in front of the x, and then square that number, that's going to get here. Okay, same process.
This is the hard way, remember?
Then, this is the hard one.
This is spoiled, we're good.
And then you're gonna distribute the 81.35 over all of that. Okay, just chill out, just chill out. So then you gotta take 81.35 times all of that. Then you've got to move an x squared over here. And then you're gonna get 80.35 x squared plus the number in front of the x plus the whole number. Then you're gonna plug that into negative b plus or minus the square root of b, okay? Into the quadratic, okay?
Imagine you like.
You can do it, but it's and if you're really into quadratics, you'll, oh, I've always loved quadratic formula.
I know this one.
So if that's your thing, okay,
Plus or minus.
you're there,
B squared
You got
minus AC over 2A.
okay, you're good.
That's in my brain.
Now here's the other way you can do it. Could I take the square root of both sides?
Yes. That would make it a lot easier.
Okay, I can take the square root of both sides. True? So, Kels, get me the square root of 81.35.
9.02.
9.02.
Yes.
So plus or minus 9.02 times 3.844 e to the 8th minus x equals x, right? Because I took the square root of both sides. So here's the other way that you can get your two possible roots. Take a positive 9.02 and distribute this. Move that x over there. You get all your numbers on one side, get your x variables on the other, solve it as a simple equation of x. To get the other root, you take negative 9.02, distribute that, combine your x's, get your answer that way. So you can either expand this and have the quadratic equation from the depths of pain and despair, or you can simply work it this way without messing through all of that. But you're going to get the same answer either way. But here's what's important. This is where you're going to get two possible roots. So L1 is going to put you between the moon and the earth. Okay, that's the center line of that ridge. L2 is going to put you somewhere out there. So one answer is going to be less than the distance to the moon. The other one's going to be a distance greater than the moon. Okay? So the idea, and there's technically like 6 different Lagrange points. You have them also out here. We're only going to do 2. Okay? So here's the basic idea of what this Lagrange point means. Is that if I could take this apple and just put it right there, what that means is that that apple would be locked in place. So even as the earth, or excuse me, as the moon pivoted and orbited around the earth, that would stay in line just like this. Same thing with your second Lagrange point out here. So if I could just stop this apple, put it right there, as the moon goes around, it would stay in that exact point as it goes around. So those are your 2 possible Lagrange points. One puts you on the inside, one puts you on the outside. Now, let me give you some hints on some of your answers, okay? So your answer to number 2 should be something times 10 to the 3rd. Your answer to number 5 should be something times 10 to the 16th. Your answer to 6C should be something times 10 to the 12th. Both your answers on 8 and 9 should be something times 10 to the 3rd.
On 9, do you have to divide by 60 to get the minutes?
Yeah. But I'm just talking about the answer that's in seconds.
Okay,
Yeah. Your answer in seconds is going to be 10 to the 3rd.
got it.
On number 12, where you're finding the mass of Saturn, that should be something times 10 to the 26th. Now, let's talk about question number 13. So, GPS satellites are parked in what we call a geosynchronous orbit. So, on a geosynchronous orbit, the orbital period is 24 hours. So this is how GPS works on your phone. So we have this parking lot of satellites that are in this geosynchronous orbit. So what that means is that if we have a satellite parked in the geosynchronous orbit above Mays High School, that means as the Earth spins, that satellite moves at the same rate that Mays High School moves. And it's going to stay directly above that point. So we have to have them, so when you're trying to figure out where you are, it's like, oh my God, I am so lost, okay? Trying to get to college, like, oh, thank God for GPS. So what happens is that your satellite is basically sending signals off. It's called a triangulation process. So your phone is bouncing signals off of these satellites, and it's triangulation of data that says, oh, you're here, okay? So, but these satellites have to be like fixed points. So that's why they have to be parked in the geosynchronous orbit. You can't use near-Earth orbit satellites because those are orbiting like every hour and a half. They're going much faster than the Earth is spinning. So we've got to move these way out here into a geosynchronous orbit. So the whole key to number 13 is that you're going to start with that Swiss Army knife equation. Big G mt squared equals 4 pi squared r cubed. You know the mass of the Earth, you're going to solve for r. Now, that answer, that initial answer that you get on 13a, is the distance from the center of the Earth out to that satellite. Okay? But the answer, but the question asks for how high above the Earth is that going to be? So this is the distance from here to that satellite. So what are you going to do to get the distance above the Earth?
Subtract the radius.
Subtract out the radius of the Earth, okay? And realistically, that's what you have to do, because like when you bounce signals, you're not bouncing a signal off of something that's in the center of the Earth. You're bouncing a signal off of something that's at the surface of the Earth, okay? That's why you have to do that. Then on 15, or 14 and 15, you're talking about the International Space Station. Okay, again, on 14, I'm asking you how high above the surface of the Earth. You're going to find r, subtract out the radius of the Earth. When you get to number 16, 16 is old school acceleration equations. Okay, they're old school. Okay, and I just kind of threw this in so you kind of stay up with that idea. So 16, old school. Okay, old school. Nothing that has to do with this. When you get to number 18, you're talking about escape velocity. So escape velocity, here's a good visual. So imagine that you're in the bottom of a gravitational well, okay? What escape velocity is how fast that has to be rolled up the hill so that you can get out of the well, okay? So that equation is not on your equation sheet. That equation for escape velocity is on that packet of notes that I gave you. So basically the only difference is that if you look at escape velocity, it's 2 big GM over R. Now eventually you'll see where this comes from because it's a function of potential energy. So it's similar to velocity. Basically the only difference is that you have a 2 in there. Okay? And on the back side of those lecture notes that I gave you, I explained what escape velocity is, and you have the equation, okay? So, just be cognizant of that. All right. Let me see. On number 15, that answer should be something times 10 to the third. Both of your answers to number 16 should be between 2 and 5. On 20, you're finding the mass of the sun if it was a black hole. That answer to 20 for that mass should be something times 10 to the 35th. So with this assignment, you have a couple of options. If you want to hand it in tomorrow, I can grade it. I'll have it back to you before the test on Monday. Okay? If you just want to hold on to it, use it to study, hand it in on Monday, that's cool too. Tomorrow we're going to spend a lot of time going over it so I can make sure that you know what you have going. So I don't care when you hand it in Friday, hand it in Monday, I don't care, okay? We're good, going once, going twice, sold, okay, stop that.